Hello, it's Ryan. This lecture is about our experimental lab write-up setup and what I'm going to be looking for in some or all of your write-ups. So this is a sample experiment. And in this sample experiment, I'm just going to use data from a previous semester because I can't obviously get this data from you. Usually I would ask the class for the data. So this is a sample experiment, and in this, we always start all of our experiments out with the purpose. So the purpose of this experiment would be, and again, this is a kind of outdated example now, but it still will do the trick for today. We want to determine the distance a typical student would drive from home to the OCC Orchard Ridge campus. So we're going to determine the distance a typical student. And the reason that we would do this, or I would ask this in class, is so I could collect the data right there in class with all of you. That's OCC Orchard Ridge campus. And so something to note would be that our purpose is a very clear, concise statement that just gives the purpose of the lab or of the experiment that we're doing. We're not even going to put anything that has to do with any procedure in the purpose at all. And actually, we're going to skip any procedure in this because I would just be asking for the data from all of you. So the next thing we're going to write is the data. And again, this would be what I'm asking you. We could have some predicted value. The predicted value I had that year was 12 miles. And this was a weird predicted value because normally or often a predicted value would be some known supported value, like the acceleration due to gravity, for example, being 9.81 meters per second squared at the surface of the Earth. That might be a predicted value in some labs, but in this one, we just had to have a kind of a guess for a predicted value. So it was a strange one, but it doesn't matter. The data that I got that year is the following. So I'm just going to write D for distance 2. So we have 3 miles, 4 miles, 4 miles again, 15 miles, 12 miles, 21 miles, and 40 miles. So that was the data I collected. And that was it for the data. We had a predicted value and then the 7 data that I got. Next, we're going to do, with this data, what we're going to do is a statistical analysis. Statistical analysis. And so you wouldn't have to put a heading like that every time you do a statistical analysis, but that's what we're doing. And so we're going to set this up first by showing sample calculations. And in all of your labs, if you have to do calculations, then you're required to show one sample calculation of each type that you do. So in these calculations, we're going to have the first being the mean value. And so we're going to get the mean value. The way we're going to do this is just like we do in our example problems from class, and that is we're going to do the general form first. So d mean is equal to, and the general form for this equation is from I equals 1 to n. This is the sum. That's a Greek letter sigma, but it stands for sum of all the distances divided by the number of distances that we have. So that's the general form. We always start with the general form, just like our problems. Now we're going to substitute our values in. We don't have to do any algebra for this. By the way, just to really make this clear, this is kind of a scary symbol, but all this is a sum, an addition, so it'd be D1 plus D2 plus D3, and now we're going to use dot notation, so we don't have to write as much. I'm sorry. All the way to dn divided by n. So I'm going to note in this one, because this is our notes, that this is dot notation, and you're allowed to use this in your write-ups. It kind of might save you some time. Now we'll substitute our values, and so we'll go ahead and input these distances. So we'll have the 3 miles plus 4 miles, and I'll just add them all together. This is the part in class where I would race the calculators, and often I would beat the calculators, and sometimes I would be pretty close to the answer, so it's all fun and games in person. And this is divided by the 7, the total. I didn't use dot notation this time, so d mean equals, and so we're going to go ahead and just put the answer in. I think it would be 99 over 7, but I think we would get 14.142857,143, and so on. And this would be in, of course, miles. But that's too many significant figures. All these numbers are significant figures, and if we're talking about a mile, I would say that this or this might be the lowest we would want to go, so I'm going to get rid of really all these for this. Who cares if you had to go an extra 0.1 mile into the to get to the school? But here's the real point. None of our some of our values up here only had 1 sig fig, but I'm not a big stickler about rules on sig figs. I'd like you to use 3 or 4 sig figs at all times in our class, unless it makes sense to use less or more, I guess. But anyway, use common sense. That's my goal, and I'll definitely catch you if I feel like you're not getting it. So there's our mean value. The next calculation we have to do is called the standard deviation. This is the one that everyone gets a little anxious over at first, but honestly, you can just have a computer or a calculator do this, all the hard work for you. But anyway, here we go. The standard deviation, we'll write the general form first. I always write standard deviation, and we're doing this in D is equal to, and we'll do the square root of, and it's a sum again, and we're going di minus d mean squared. And this is all divided by, which is still under the square root though, but this is all divided by n minus 1. So make sure it's obvious that this n minus 1 is also under the square root. Students often forget to do that. Now we could, of course, write this in with dot notation just to get you all thinking this way. So this would be d1 minus d mean squared plus d2 minus d mean squared plus d3 minus d mean squared, and then we would use dot notation and dn minus d mean, and that's all divided by n minus 1. Now we can go ahead and substitute the values in. This is going to get kind of ugly. This is definitely a place where you would probably want to use dot notation, but we can go ahead and I'm going to do it. I'm going to save us some time. Who wants to watch this? So we'll use it. Here we go. It was 3 miles minus 14 miles squared plus 4 miles minus 14 miles squared plus 4 miles minus 14 miles squared plus, and we'll do the dot, dot, dot. And then our last value, I believe, was 40. So we had 40 miles minus 14 miles squared. And then we're going to divide by, well, 7 minus 1 quick. Of course, it's 6. Okay, well, this So the standard deviation and the distance would be 13.2 miles, which is pretty large. Okay, our next calculation would be the percent difference. And because I can't talk as much with you, I'm just going to add a little note in here for percent difference. Percent difference always indicates the accuracy of something. So percent difference will indicate the accuracy of an experimental value. So our general form for the percent difference, I always write percent difference equals, and it goes d experimental minus d predicted divided by d predicted times 100%. So if we substitute our values, the percent difference will equal, and our experimental value was 14. It was actually 14.1 miles. And we're going to subtract the predicted value, which was the value given at the top, which was 12 miles. And then we'll divide by the 12 miles because it was predicted, times 100%. And this will yield a percent difference of 17.5%. And we'll note that if the percent difference, the absolute value of it, is less than 10%, then we would say that the experiment was accurate. Then we can claim accuracy. So in this experiment, we weren't accurate. That's okay. Finally, the last calculation we would like to do is a percent deviation. Percent deviation. The percent deviation equation is equal to the standard deviation divided by the mean times 100%. So that would give us the percent deviation. We would show the 13.2 miles divided by the 14.1 mile times 100%. Percent deviation is equal to, and that would give us a 93.6 approximately percent. And let's make our note here. Let's get our answer highlighted. So let's note that percent deviation will dictate if we were consistent when we, did the experiment. So percent deviation will dictate if we were consistent. Maybe I could have said illustrate, but anyway, the condition, percent deviation, should be less than or equal to 5%. And if that's the case, then we can say that the experiment or the data was collected with consistency. Data collected with consistency. And it's funny, consistent doesn't have an A in it. So keep your eye out for that. Okay. Something interesting, just so you know, the standard deviation in general, this gives us, it's a very powerful tool. And so in general, when we look at standard deviations, it'll create curves, and most of the data, usually about 70% of the data or more, will fit within the bell curve of that. And so we're going to kind of see that with our data, I bet, but it's just something interesting about standard deviations. So, okay, so that was all of our calculations. Now we're going to show results. And the way we're going to start our results out is with a graphical presentation. And this graphical presentation is really, we're going to use a typical line graph. So I'll say using a typical line graph. And so this line graph, we'll always label our axes of any graph we do with a label in units. And if I write a unit on the axis, then I don't have to write the unit over and over again. For each number. Anyway, so I'm going to label first the mean value. The mean value was 14.1, so that's probably about here. Maybe a little over. Maybe here. D mean. And then I'm going to also show to the left of D mean, I'm going to do D mean minus the standard deviation in D. And that's going to end up giving us 0.9 miles. And so we'll show that is about here. And on the right side, we're going to do D mean plus the standard deviation in D. That'll end up being about 27.3. That'll be about here. And they should end up evenly spaced around the mean value. And so all of our data should end up falling in this range. Well, about 70% of our data will end up falling in that range. And so this classifies the power of a statistical analysis really is that I would argue that this classifies the typical distance that any student would drive to OCC, any campus, and all I did was survey 7 people in the class. And so normally I'd give an extra credit assignment with this, but I've worked the extra credit into the first lab. So we'll continue our results section. Once we do our graphical presentation, we can show the rest of the results. We want to put anything we had to calculate in results. So we had D mean. That was 14.1 miles. We had the standard deviation in D. That was the 13.2 miles. We had the percent difference and percent deviation. And we had a predicted value. I guess that really was in data. But I'm just going to put it in. So there are all the numeric results that we had to calculate. And we could just, you could note that we were not really accurate or consistent, but there wasn't a lot we could do about that. So that is an example of a sample of a statistical analysis. And a really important point to end this with would be we can say that standard deviations work with 7 data or more. If we have less than 7 data, they don't really mean very much. So anytime, so I'll just write this. Anytime you collect 7 or more data, you have to do a statistical analysis in your labs. It's how we analyze if our experiment was successful or if we supported or disproved something. It's very important. But you must have at least 7 data, or else you really can't do any of these calculations except a mean and perhaps a percent difference. So you have to have 7 data or more in order to do those. Okay. Well, I wanted to add, I'm adding this to the D2L site for you. This is a lab report format. This lays out in general what I'll be looking for, and it has some of the equations we just used. So you can read this at your leisure. There is one addition I'd like to add to this, though. For all of your lab reports, so we might just write this down here. So for this semester, anytime you submit a lab report, I'm not going to write it. I'll just tell you and I'll make an announcement. Anytime you submit a lab report, you must include a picture of some kind that shows you with your experimental setup that you're using. It doesn't have to be an amazing picture or anything, but I just need to have some sort of proof that you guys are all doing these experiments. And so that's kind of the way I decided to do it. A little selfie with you and your equipment, and that you could use for your procedural diagram, which would usually go along with the procedure, right, described here. So anyway, don't forget a selfie would be good, just so I can have some proof that you're doing these reports or that you're doing these experiments yourself. Great. Thanks for watching. I'll talk to you all soon.